For decades, producing hydrogen required large, custom-built chemical plants, multi-year engineering schedules, and massive infrastructure footprints. But that era is ending. A new wave of technologies is reshaping how developers deploy hydrogen systems. Not at the gigawatt scale first, not through mega projects only multinationals can afford, but through modular, factory-built electrolyzer units that ship like appliances and plug directly into renewable energy. This shift is as significant for hydrogen as the shift from custom-built solar installations to modular solar panels was for the solar industry. And today we're going to explore this breakthrough in depth: what modular electrolyzers are, why they matter, how they're transforming deployment speed, who is leading the innovation globally, and what real-world examples tell us about the future of hydrogen deployment. To understand why modular electrolyzers are so important, we have to step back and remember how hydrogen projects used to be built. Historically, developers began with detailed engineering studies, custom site layouts, long procurement processes, and multi-year civil works. Every hydrogen plant was almost a bespoke creation. Electrolyzer stacks needed their own buildings. Power electronics had to be engineered from scratch. Water treatment and compression systems were custom integrated, and commissioning could take years. This approach made hydrogen production slow, expensive, and only realistic for very large players. It also made risk extremely high, because any miscalculation or delay could push a project millions over budget. Modular electrolyzers flip this model on its head. Instead of building a large plant designed from scratch, you deploy standardized, pre-assembled units that function like Lego blocks for hydrogen. These units are constructed in factories, integrated with power electronics, sensors, compressors, cooling systems, and control logic. They are then shipped to project sites in containers or skid-mounted platforms. Developers simply plug in electricity, water, and hydrogen output lines. No buildings, no multi-year civil works, no bespoke engineering, no complex integration. And the biggest advantage of all, to scale, you simply add more units. One of the clearest examples of how this revolution is taking shape comes from Denmark, where Stiesdal Hydrogen has introduced what they call the hydrogen block. It's essentially a complete hydrogen production plant in a modular box. Each block provides around 3 megawatts of electrolyzer capacity, wrapped into a compact, test bench verified, ready-to-install unit. These blocks include not only electrolyzer stacks, but also water treatment, gas handling, power electronics, cooling, and control systems. Everything you normally find spread across a large facility. Stiesdal designed these blocks so that a developer could deploy 1 or 2 units to begin with, and then scale to 12 megawatts, 24 megawatts, or 50 megawatts, simply by adding more blocks. This transforms green hydrogen from a capital-intensive megaproject into a modular, gradual investment that can grow with demand. Germany is also playing a central role in the modular electrolyzer frontier. H-TEC Systems, one of Europe's fastest-rising hydrogen technology companies, has designed a modular hydrogen platform, a series of standardized 10 megawatts building blocks that combine into systems exceeding 100 megawatts. Unlike bespoke electrolyzer hulls, each H-TEC unit arrives pre-assembled from the factory, including its thermal management, water processing, and DC power systems. That means developers need only minimal site preparation and can commission plants far faster than traditional hydrogen builds. H-TEC's system efficiency and pressure handling make it suitable for industrial clusters, refueling stations, steel production pilots, and energy storage hubs. The concept is simple. Instead of building a 100 megawatts electrolyzer facility, you buy 10 megawatts units that fit together seamlessly. The United States is quickly emerging as a leader in modular electrolyzer technology, with companies like Verdagy pushing the frontier. Their design focuses on modularity and the ability to react instantly to renewable energy fluctuations. Verdagy's eDynamic system can ramp from full power to very low power within minutes, which is essential when operating on solar or wind energy where supply constantly changes. Their electrolyzer uses a large single-cell architecture housed in modular frames that can scale from about 20 megawatts to more than 200 megawatts. These units run at high current densities while maintaining strong efficiency and durability. A key advantage is maintenance. Instead of shutting down an entire electrolyzer stack, Verdagy allows individual cells to be serviced independently. This minimizes downtime, lowers operating costs, and makes continuous hydrogen production far more practical and reliable. Another frontier of modular electrolyzers comes from Japan, where companies are integrating electrolyzers into mobility hubs and transit infrastructure. Osaka Metro recently installed a system that uses solar power to generate hydrogen on-site, using a compact modular electrolyzer, with the hydrogen fed into a stationary fuel cell to support the operations of a transit depot. While this deployment is modest compared to larger industrial projects, it demonstrates the value of modular systems. Hydrogen production can now fit into small footprints, urban settings, and distributed grids. Australia is also emerging as a leader in modular electrolyzer adoption. Companies such as Hydrogen Systems Australia and Provaris are exploring modular hydrogen units to support remote mining operations, agricultural hubs, and off-grid communities where infrastructure is limited. Australia's vast solar resources make modular electrolyzers an ideal way to convert remote solar energy into hydrogen without building large facilities. These smaller units allow developers to test local hydrogen markets, supply hydrogen-powered equipment, and expand gradually. Meanwhile, in the Middle East, countries like Oman and the UAE, traditionally home to large-scale hydrogen megaprojects, are exploring modular electrolyzers for early-stage pilot deployments before building full-scale ammonia export facilities. These pilots help test renewable integration, water supply logistics, and hydrogen handling infrastructure. Modular units make this possible without waiting years for mega-project construction to complete. What ties all these global examples together is a single theme. Modularity unlocks speed, flexibility, and lower risk. A modular hydrogen system can be purchased, shipped, installed, and commissioned in a matter of months, sometimes weeks. This contrasts sharply with the traditional model where a hydrogen facility might take 3 to 5 years to complete. And lower deployment time correlates with major financial benefits: quicker revenue generation, reduced cost of capital, and minimized exposure to policy changes, permitting delays and supply chain disruptions. Now, let's examine why modular electrolyzers represent not just an engineering shift, but a fundamental business model transformation. Traditional hydrogen plants demand large upfront capital investments. In many regions, this creates financial risk too high for small developers, agricultural cooperatives, microgrid operators, or startups. But modular electrolyzers let you start small, for example, deploying a single 3 megawatts or even a 1 megawatt unit, and expand only when off-take agreements solidify. This incremental deployment dramatically improves project bankability. Furthermore, modular electrolyzers reduce the hidden, soft costs associated with hydrogen production. For traditional plants, engineering, site design, custom balance of plant integration, and multi-layer permitting make up a significant percentage of total project costs. Modular units eliminate most of this because the balance of plant is pre-integrated and standardized. These systems reduce engineering uncertainty and create reliability through repetition. Every unit built in the factory has identical components, identical wiring, identical fluid handling systems, and identical control software. Factory standardization leads to higher reliability and lower O&M costs in the field. The next major advantage of modular systems is geographic flexibility. A traditional hydrogen plant requires a large site, access roads, a high-voltage grid connection, and significant water supply. Modular electrolyzers can be placed in remote areas, on brownfield land, next to renewable farms, near industrial off-takers, or even inside logistics yards or ports. Because modules can be arranged in clusters, hydrogen production can be scaled for precise local needs without overbuilding infrastructure. For example, mining companies in northern Canada have begun investigating modular electrolyzers to fuel off-grid equipment. Remote areas in Namibia, Chile, and South Africa, with excellent solar resources, can deploy modular units long before national hydrogen infrastructure is complete. When comparing modular electrolyzers with other emerging hydrogen technologies, such as panel-embedded hydrogen systems like Solhyd or nanostructured photoelectrochemical devices like Sun Hydrogen's modules, the differences are clear. Panel-based systems seek to decentralize hydrogen production at the panel level. Artificial photosynthesis seeks to reinvent the reaction pathway itself. Modular electrolyzers, on the other hand, seek to industrialize, simplify, and accelerate the deployment of the proven electrolysis pathway. They do not reinvent chemistry, they reinvent deployment. That's why modular systems will likely dominate the near-term market, even as panel-based and artificial photosynthesis technologies continue advancing. One of the more fascinating implications of modular electrolyzers is how they enable mid-scale hydrogen markets that previously did not exist. For example, hydrogen for regional trucking hubs, airports, fertilizer producers, small chemical plants, and agricultural cooperatives can now be produced locally instead of relying on massive centralized plants. This decentralization is a major part of the emerging Hydrogen Valley concept in Europe, where local ecosystems combine production, mobility, heat, and industrial use. Modular electrolyzers are the backbone of these ecosystems because they allow developers to match capacity to demand growth. We are also seeing early signs of standardized hydrogen microgrids, where modular electrolyzers pair with solar PV, battery storage, and hydrogen tanks to provide 24/7 off-grid power. This is extremely promising for islands in the Pacific, remote African villages, and disaster resilience hubs worldwide. Instead of building diesel generators or expanding grid lines, microgrids can install a few solar arrays, batteries, and modular electrolyzer fuel cell systems to create a stable mini-grid. So what does all this mean for developers, consultants, and investors? It means that the hydrogen market is finally gaining the infrastructure flexibility needed for widespread adoption. Modular electrolyzers reduce the three biggest barriers to hydrogen: time, cost, and complexity. They create predictable project templates, enabling faster financial modeling and better risk assessment. For your hydrogen project starter kit, these systems fit perfectly into your financial modeling frameworks because they provide known costs, known performance parameters, and repeatable scaling patterns that make long-term forecasting more reliable. In the next decade, the companies pushing modular electrolyzers, Stiesdal, H-TEC Systems, Verdagy, Nel Hydrogen, Plug Power's modular PEM units, and emerging startups across Asia, will likely define the backbone of the world's hydrogen infrastructure. Meanwhile, regions like Europe, California, Australia, Japan, Chile, and the Middle East will serve as global laboratories for deployment. And as modular designs continue to improve, we may see cost reductions similar to what solar PV experienced in the 2010s. The hydrogen revolution will not happen through one giant project. It will happen through thousands of modular units deployed everywhere, from ports to farms, from factories to microgrids, from mining sites to transit depots, and it is happening now.